All right. Well, thanks very much, and thanks very much to the organizers for the opportunity to speak here. So I'll be talking about some work together with Alex May and Sabrina Pastersky at Perimeter Institute, as well as Michelle Xu at Stanford. And the subject of a lot of my talk is going to be tensor network models for holography. And the reason I'm going to spend so much time talking about them is because these models have given us a lot of valuable insight into various information theoretic properties of ADS-CFT. So some of the most obvious successes here are that these models have avatars of things like the Ryu-Takayanagi formula and entanglement wedge reconstruction. And a lot of these information theoretic properties have this nice feature that they're amenable to direct verification in genuine gravitational theories. So in that context, these tensor network models are really best thought of as being useful as kind of computationally explicit toy models for genuine holographic maps. So for example, something like the Ryu-Takayanagi formula, you can argue for directly on the basis of the gravitational path integral without appealing to any intuition from tensor networks. Now, since at least kind of the work of Harlow and Hayden, it's seemed increasingly clear that probably computational aspects of quantum gravity are going to be playing a very important role in reconciling quantum mechanics with a semi-classical description of gravity. This is probably particularly true in the presence of black holes. So given the successes of these tensor networks for understanding information theoretic properties of ADS-CFT, it's kind of natural to try to apply them to certain computational questions about the holographic map and to see what predictions they make for something like the complexity of bulk reconstruction. So in particular, it's been argued that for spacetimes that contain a Python's lunch, whose associated tensor network involves some amount of post-selection, it seems to be the case that bulk reconstruction should be exponentially complex in 1 over g Newton. But unlike a lot of these nice information theoretic properties, this kind of complexity theoretic question is a lot more difficult to address in these bona fide theories of quantum gravity. So it's very difficult to come up with something like the path integral calculation to check this kind of conjecture. And maybe the best evidence for this Python's lunch conjecture comes from arguments in favor of a kind of converse statement that bulk reconstruction outside of Python's lunch should be simple in some sense. Okay, so in my talk here, I'm going to try to bridge this divide by inferring certain consequences of the post-selections in these tensor network models for boundary correlation in ADS-CFT. So for people that are familiar with this connected wedge theorem of Alex and friends, the motivation is going to be quite similar to that story. So somehow the idea will be to embed some causally constrained information processing task into a holographic CFT. And then argue that in order to complete this task, it's necessary that certain parties in the CFT would have to share sufficient correlation. Then we use the bulk perspective, where you might have extra access to this sort of favorable causal structure in the bulk to complete the task. We'll use that perspective to argue that there should exist a protocol to complete the task in certain cases, and then we can infer from that different CFT regions must have shared sufficient correlation. An extra input in our situation is going to be a prediction coming from tensor networks for the success probability of a low complexity reconstruction for an operator inside the lunch. And so together, all of these ingredients will lead us towards some conjecture for some strictly geometrical constraint on holographic spacetimes, and we'll give at least some preliminary consistency checks for this. Okay, great. So a brief outline. First of all, we'll talk a bit about these tensor network models and this Python's lunch conjecture that comes from these models. Then we're going to take a detour and talk a bit about quantum cryptography and this cryptographic primitive called the conditional disclosure of secrets. And then we'll come back to gravity and combine the previous ingredients to try to arrive at this conjecture. Okay, so tensor networks. So the setting for a lot of what I'm going to talk about in this first part of the talk is going to be some holographic tensor network, which we can think about as some map from some bulk state on some bulk Hilbert space to some state on some boundary Hilbert space. It's in general, say, some bipartite state. So in this kind of figure, which you'll see a lot of, these little blue boxes correspond to tensors, and the black lines are different factors of the Hilbert space for the inputs and outputs of these tensors. These red dots correspond to different factors of the bulk Hilbert space, and the little dots on the peripheries correspond to different tensor factors for the boundary Hilbert space. And just for convenience, we'll assume throughout that all of these individual constituent tensors are just going to correspond to some random tensors. So some Haar random unitaries, and then possibly with some ancillas or some post-selection. and everything, like all of these individual tensor factors, we'll just assume they all have the same dimension d. Okay, and the kind of question we'll be interested in is a question about bulk reconstruction. So we want to ask about bulk reconstruction on some subset of the boundary, say the right part of the boundary. And this is supposed to be analogous to some question in gravity about reconstructing some portion of some spacetime in ADS-CFT given access to just part of the CFT, the reduced state on part of the CFT. So in order to characterize what region of the bulk should be reconstructible, we have to have some analog in the tensor network of a Ryu-Takayanagi surface. And this analog is going to be this RT cut. So this is some cut, which is homologous to the boundary region R, some cut through the network, which minimizes some kind of generalized entropy. So this is a lot like the usual gravitational generalized entropy. There's something like an area term that's counting like the number of legs that we're cutting through, and something like a bulk entropy term, which is some notion of entropy associated with the bulk degrees of freedom on this homology surface for the cut. So it's shaded green in this top figure here. Okay, and then so the statement of entanglement wedge reconstruction is going to be something like this. So we'll be interested in a situation where our code subspace just corresponds to all of the entire bulk Hilbert space in this kind of picture. And then entanglement wedge reconstruction tells us that some local bulk operator O is going to admit a boundary reconstruction on the right half of the boundary Hilbert space, provided it lies in the entanglement wedge associated with R, where we're thinking about the entanglement wedge or the RT surface associated with the maximally mixed state in the code subspace. So in that case, one has some approximate isometry that maps from the Hilbert space associated with this cut on the RT cut and this bulk Hilbert space to the right of this RT cut into our boundary region R. Now, okay. We're going to now suppose that we're in some situation where there exists another cut, which is a local minimum of this generalized entropy. So we call this the appetizer, or we don't call it, someone called this the appetizer. And it satisfies this property that the generalized entropy is larger than the generalized entropy associated with this RT cut, even though they're both local minima. So I show an example of this in this figure. And so this is supposed to capture some situation in gravity where we have multiple quantum extremal surfaces that are homologous to this boundary region, including some new surface which it has got larger generalized entropy than the RT surface. So now we're going to use sigma PL to denote this subset of the bulk degrees of freedom that lie between these two cuts. So this is the so-called Python's lunch. And yeah, so in a lot of the following, we'll just zoom into the part of the tensor network that maps from this cut to this cut. So it maps from the RT surface, the Hilbert space on the RT surface, and the bulk Hilbert space inside this Python's lunch into the Hilbert space associated with this appetizer cut. Great, okay. Now this kind of like restricted part of the tensor network, which I'll call V, it's assumed to be globally isometric or approximately isometric. But nonetheless, the fact that we have multiple local minima of this generalized entropy reflects the fact that not all of the individual constituent tensors in this network are themselves isometries. So in particular, we have to have some post-selection in order to get this, these extra local minima. So yeah, again, we can recall that these individual tensors might have some ancillas or some post-selection. And so we'll let ML denote the total number of ancillas in this part of the network, so the number of qubits coming in on the right. And MR is going to denote the total number of post-selections. Now, okay, we can get to with all of this background, we can get to the actual Python's lunch conjecture. So the complexity of implementing this part of the tensor network, we expect that it should be no larger than exponential in this total number of post-selections MR, because we can just imagine like attempting to perform the post-selection by just, applying the network and then measuring and hoping that we get the right outcome. And it's going to take at most exponential in the number of post-selections, number of attempts, before we can be assured that we'll have a success probability, which is order 1. In fact, the original authors of this Python's lunch paper provide some Grover-inspired procedure which constructs some unitary U hat, which is able to implement this V on all of the relevant input states in the code subspace, and its complexity, the log complexity is actually half of what we got from this naive argument. So the log complexity is just the number of post-selections divided by 2. Some caveats are that this is assuming that like certain properties of this tensor network. It should be sufficiently scrambling, and it should have this parametric hierarchy between the number of ancillas and the number of post-selections. And another short comment is that we noticed that having constructed this unitary U hat, which implements this tensor network, we can just apply the inverse of this unitary in order to reconstruct some bulk state given some boundary state and promise that we're in the code subspace. So this quantity actually is also just the reconstruction complexity, the complexity of the reconstruction task where we're given some boundary state in the code subspace and we have to reconstruct what the bulk state was. Okay, so yeah, that's the statement of the Python's lunch conjecture, that we have a complexity which is like exponential in this number of post-selections divided by 2. Now we can ask, in gravity, what's the geometrical analog of this amount of post-selection? So in the tensor networks, a useful way of characterizing this amount of post-selection is that it's just the difference in the log dimensions for the Hilbert space is associated with 2 cuts, which we call the bulge cut and the one we already met, the appetizer cut. Or equivalently, it's just going to be the difference in generalized entropies associated with these 2 cuts. So this is a useful way of characterizing this amount of post-selection because it makes it clear what the geometrical analog should be in ADS-CFT. So we expect that the gravity analog is just going to be the difference in the usual gravitational generalized entropy associated with 2 different surfaces which are homologous to this boundary region R. So some bulge surface and then some locally but not globally minimal surface, the appetizer. And then the Python's lunch conjecture in gravity says that the complexity of reconstructing some bulk operator inside the Python's lunch or past this appetizer surface is going to be exponential in this difference of generalized entropies divided by 2. Okay, so we kind of said that this amount of post-selection should be related to the size of some bulge surface, but how do we actually formally define this bulge surface? So in the tensor network case, we intuitively see that this bulge cut is supposed to represent essentially the maximal width of this tensor network. And one way to make that a little more explicit is to think about defining the bulge by doing some maximization over cuts and some sweep out through the network. So some family of cuts that interpolates between like the RT cut and the appetizer cut. But to make sure that procedure isn't kind of like dependent on the sweep out in a way that gives us like an unnaturally wiggly bulge, we should also then perform some minimization over possible sweep outs. And that's going to land us on the appropriate cut. So the kind of analogous thing proposed by the authors of the Python's lunch paper in ADS-CFT is to imagine that we have some partial Cauchy slice for this Python's lunch region, whose boundary is the union of the appetizer surface and the RT surface. And we'll think about a sweep out as corresponding to some function from this partial Cauchy slice into this interval 0, 1. And that's going to define a sweep out essentially via level sets. So, the inverse image of some number in that interval is going to correspond to some surface in the bulk that has the appropriate homology. And then in this context, this bulge surface is going to be defined by a maxi-mini-max procedure, where for some sweep out, we identify like the largest area curve in the sweep out. Then we do a minimization over sweep outs, and finally we have some maximization over different possible partial Cauchy slices. Now, okay, so with those kind of nice covariant definitions of all of these relevant surfaces, we can talk about some useful space-time regions that are going to appear throughout our discussion and that have an interesting physical interpretation. So given some boundary region, R hat, this is some picture where we have some bulk space-time and then some CFT and some boundary region, R hat. The easy wedge associated with R hat is just going to be the domain of dependence of the homology surface for the appetizer surface. So in this picture, it's just this shaded purple wedge here that ends on this appetizer surface. And so in particular, this is the portion of the entanglement wedge, in general some subset of the entanglement wedge, which is easy to reconstruct, assuming the Python's lunch conjecture is true. On the other hand, operators that are in the entanglement wedge, but outside of this easy wedge, are expected by the Python's lunch conjecture to have a reconstruction complexity which is exponential in this generalized entropy difference divided by 2. So these are operators that are inside of this shaded entanglement wedge, but outside of this smaller easy wedge. It'll also be convenient for our purposes to define this not easy wedge. So this is just some notation. It's referring to the space-like complement of the easy wedge. So this purple region here, which in general will include some things inside of the entanglement wedge, so things that are complex to reconstruct, but not information theoretically impossible. It'll also include some region of the space-time which is not possible to reconstruct. Yeah. Yeah, it is. Yeah, sorry, I should probably call it that, but yeah, it's the same. Great.
Is the easy wedge the same as the causal wedge?
In general, no. In general, this easy wedge will be larger than the causal wedge. Yeah. So the easy wedge is defined by you have a bunch of QESs associated with this boundary region. You choose the outermost one. It turns out that there is always a unique outermost QES, and so yeah, by thinking about the domain of dependence of the homology region associated with that QES, we define this easy wedge. Thanks.
Maybe a naive question. So when the appetizer is equal to the bulge, and you get 0 on that formula, you still expect a large complexity on reconstruction, no? And so
I don't think the bulge should ever be equal to the appetizer because. Oh, you're saying they're different surfaces in principle, but
it would be symmetric, no?
Yeah, I think like these surfaces are defined, like the bulge is not a locally minimal surface and the appetizer is a locally minimal surface, so they can never coincide.
So it's only valid for those situations, basically, the conjecture.
This formula is valid for a situation where you have more than one locally minimal quantum extremal surface. And so in that setting, I think it should always be the case that this will have larger area than this. So
I don't see that.
Yeah.
That's my question, basically. Maybe I'm missing something, but I don't see that in gravity. Why?
Yeah, you're right. That's not super obvious.
It doesn't follow from the maxi-minimax prescription? You have two minima intuitions and you have a maximum.
Yeah, you're right. So it follows from the maximum. So it turns out that this bulge surface is picked out by this maxi-mini-max prescription, where you fix the appetizer on the RT surface and then do this maxi-mini-max. So that is to say, it'll never have smaller area than the appetizer. It's kind of an edge case whether it could potentially have equal area. But yeah. Great. Okay. Thanks. Any other questions? Great. Thanks.
Unless every surface that interpolates between the appetizer and your supposed RT surface has exactly the same area.
Yeah.
In which case you don't know what the RT surface is, you're in a phase transition, and you know that various other corrections can be allowed.
Yeah, that sounds right. Thanks. Okay. All right, so much for the Python sludge conjecture. We'll now move on to kind of a different consequence that we're going to argue for post-selection in these holographic tensor networks. Okay, so somehow we established with this Python sludge story that we can't learn much about the inside of a lunch if we only have access to low complexity operations, assuming this Grover method is optimal. But we can still presumably learn something about the lunch. So we're going to imagine this kind of a task. So suppose that we'd like to learn about some subset, sigma x, of the total bulk degrees of freedom inside of this Python's lunch, sigma PL. So, and for simplicity, we're just going to assume that we're promised that the the bulk state is just some computational basis state which is chosen uniformly at random. So that's some promise that we're assuming here. And now to make sure that we have a high probability of reconstructing the correct bulk state with high fidelity, we know in general of no better strategy than just applying this high complexity, inverse Grover unitary that we were describing before, and then doing a measurement to infer what the bulk state was. But it turns out there's a much lower complexity procedure which can still yield a very small bias towards the correct answer. So this procedure works like this. So yeah, we're given this setting where we have some subset sigma x that we'd like to learn about. And now what we're going to do is we're going to imagine the space, like all possible cuts gamma x, which lie before this subset of the bulk degrees of freedom and have the appropriate homology. So in other words, all of the cuts such that the sigma x that we'd like to learn about is a subset of the homology surface associated with this gamma x. And now from within the space of cuts, we're going to choose some particular cut, which we'll call gamma x bulge, or the restricted bulge cut, which is going to minimize the number of projections MR prime that we encounter in this restricted tensor network, mapping from this cut gamma x into this cut gamma appetizer. So we have this full tensor network describing the Python's lunch between this RT cut and this appetizer cut. We're thinking about all possible cuts that occur before this subset sigma x, and now we're choosing the one which is going to minimize the number of post-selections that we encounter in this restricted map. So this restricted map we can think about as just corresponding to some tensor network unitary along with some post-selection. In this example, the tensor network unitary is just the single constituent unitary u of x. And okay, it's probably a bit difficult to see, but the number of post-selections in this case is just 2. We're post-selecting on 2 qubits here, even though the total amount of post-selection in this Python's lunch can be larger. And now, okay, to estimate the bulk state on this sigma x, what we're going to do is just apply the inverse of this u of x. So that's what we're doing here. And then we're going to do a measurement of the bulk degree of freedom in the computational basis state. And so that's kind of the procedure I'm showing in this bottom right-hand corner. So we take the state on this cut, we add the appropriate number of ancillas, we do the inverse of this tensor network unitary, and then we just do a measurement in the computational basis state. And the point is that we get an answer. We get an answer which is biased towards the correct answer, and the bias in the success probability is exponentially suppressed in this restricted number of post-selections MR prime. So in particular, this, unlike for the full number of post-selections in the Python's lunch, this bias is going to depend on the exact, location and size of this sigma x. Okay, so now we want to come up with a nice geometrical way of characterizing this restricted number of post-selections. So this number of post-selected qubits MR prime, it should again be seen as a difference in generalized entropies between 2 cuts, this time between the appetizer and this restricted bulge cut. And whereas the usual bulge we defined with respect to sweepouts which cover the full Python's lunch, in this case we're allowed sweepouts which only need to cover the portion sigma x of the Python's lunch that we're interested in reconstructing. So this definition is capturing the idea that we only require the cut to appear before sigma x instead of before all of the post-selections in the Python's lunch. Okay, so now we can ask about a related question in ADS-CFT. Oh, sorry.
Sorry, Chris, about the previous slide. Yeah, so are you guaranteed that there is a maxi-minimax surface even if you restrict to only the portion of Python's lunch that you're interested in?
You're asking about the existence of...
Yeah, what I'm asking is basically you have this other cut in the tensor network that you consider this like a constrained cut on only a piece of the Python's lunch. Are you guaranteed that exists in gravity, like even if you don't look at the full Python's lunch?
That it exists in gravity, or?
Let's say here you can just define a cut, I guess, but what you would like to do is some maxi-minimax, I guess, like some maxi-minimax procedure on just the portion of Python's lunch that you're interested in. Are you guaranteed that one such surface exists?
I expect that you are. Like in particular, like well, it seems like this maxi-minimax procedure is as well defined as the maxi-minimax procedure that defines the usual bulge surface. So
Okay.
I don't expect any new issues with existence in this case.
Okay, great.
Yeah.
Thank you.
Oh, sorry. Okay, so yeah, now we want to ask about kind of the gravity version of this statement. And it's useful to consider a situation which is going to be well motivated, from the perspective of what we want to do later on in the talk. So yeah, we're going to imagine that we have some secret, which is localized in this space-time region X. And we'd like to try to imagine that, we're trying to hide the secret from some low complexity agent associated with the CFT region R by throwing the secret into the, not easy wedge associated with R. So given X, we can try to hide it from this low complexity observer here by throwing it into this, in general, difficult or impossible to reconstruct wedge. And so we'll let this big X denote the, the intersection of the future of this region with this not easy wedge. So it's the part of the easy wedge that you could potentially hide the secret into. Yeah, so for this type of space-time surface, we'll also denote for a partial Cauchy slice sigma, we'll let sigma X denote the intersection of that slice with this bulk space-time region. And now what we're going to do is we're going to define a restricted bulge surface associated with this space-time region X via a maxi-minimax procedure like the one that we were just describing. So the only difference between this maxi-minimax procedure and the usual one is that now we're allowing for a maximization, well, we're allowing for sweep outs which only cover a part of the, partial Cauchy slice associated with the Python's lunch region. So yeah, without getting into too much, notational details, that's the statement, is just we're now allowing for kind of a more general class of sweep outs. And the proposal then is that the analog of this, restricted amount of post-selection in this gravitational context is just some difference in generalized entropies, which I'll call delta SX gen, between this restricted bulge surface defined by this maxi-minimax procedure and some appetizer surface. Okay, so the upshot of all of that is that the claim here is that when a Python's lunch exists, we've proposed some sort of covariant quantity, this generalized entropy difference, which would be purely geometrical in the semiclassical limit, and it should control the, in general, exponentially small success probability of some low complexity reconstruction procedure. So in a moment, we're going to try to relate this quantity to boundary correlation appearing in ADS-CFT. But first, we're going to take a detour and talk about a particular cryptographic primitive. But maybe I'll stop and ask if there are some questions first.
Can you just explain the first part of your last slide again? The physical motivation here. I wasn't sure what you meant by the secret is at little x, and you're going to throw it into the.
Yeah, sorry. Fair enough. I was trying to have some physical motivation for defining some bulk space-time region, which is a subset of this hard-to-reconstruct wedge.
But that's really the input. The capital X is the input to your problem. You just assume that your secret is in the region capital X, and you start. I shouldn't worry about little x propagating into the easy wedge. And
yeah, you shouldn't worry about that. That's right. The big X is supposed to be the largest part of this hard-to-reconstruct wedge that you could, in principle, put the secret into. But yeah. Thanks. Yeah, hopefully that, the reason I tried to state it that way will hopefully be clear later on. Okay, so moving on to cryptography. Okay, so this might seem a bit unrelated from the progression that we were just taking, but hopefully it will become clear shortly. So this conditional disclosure of secrets, or conditional disclosure of quantum secrets, is some cryptographic primitive, which will turn out to be useful. And so to define a CDQS, we have to imagine specifying some binary function f, which maps from two n-bit classical inputs into a single classical bit, as well as specifying some other parameters in the problem. So nq is going to be the number of qubits in the secret that we will attempt to hide using the CDQS. And then we also have some parameters epsilon and delta, which are going to characterize this CDQS. But the basic idea is that we say that something is a CDQS protocol, or sorry, the definition of a CDQS protocol will be that for this choice of F, NQ, and epsilon and delta, there exist quantum channels A and B, and some quantum state psi, which can be used as follows. So we imagine that we have a situation with three parties, Alice, Bob, and some referee. And Alice and Bob are kind of like attempting to fulfill some task defined in terms of this data I just mentioned. So Alice and Bob can be assumed to each receive some n-bit classical input. Alice receives X, Bob receives Y. They don't know what input the other one is receiving. In addition, Alice receives some quantum secret, which is unknown to Bob. And then Alice and Bob are allowed to share some quantum mechanical resource state, psi LR. And then Alice and Bob are going to apply, what it means for Alice and Bob to have a CDQS protocol is that there exist channels A and B that they can apply, which are allowed to depend on their respective classical inputs and some choice of resource state so that they're able to achieve the following. Using these channels, they can generate some quantum messages, which they then send to a referee. And so in correct instances, meaning situations where F evaluated on these classical inputs X and Y evaluates to 1, we require a correctness condition, which is that the referee should be able to reconstruct the secret with high fidelity. So specifically, there exists some decoding channel that the referee can apply to the messages they receive in order to, reconstruct the secret to epsilon good approximation. On the other hand, for secure instances where this F of X and Y evaluates to 0, we require that the referee shouldn't be able to learn anything effectively about the secret. So in particular, one way of phrasing this is to say that there exists some simulator channel that has no information about the secret. This full channel corresponds to just tracing out the secret entirely and then applying the simulator channel. And that should look like the message generated by Alice and Bob in these secure instances to delta good approximation. Okay, so that's the definition of this primitive and what it means for Alice and Bob to have a protocol to complete CDQS for this choice of parameters. I'll note in passing that this delta appearing in the security requirement is naturally thought of as like the maximum bias in the referee's success probability in these secure instances where they're not supposed to be able to learn anything about the secret. Okay, so just to really focus on what the actual challenge is here, the challenge is that somehow Alice has to decide whether or not to send the secret without actually knowing what Bob's classical input was. So for a general function, it seems like you'd need to know both of the classical inputs in order to figure out whether you should send the secret or not. Nonetheless, it turns out that there's always some strategy to perform this task regardless of the choice of function f. So as a simple example, we'll just imagine, n equals 1, we just have a single classical bit as a secret, and we choose f to be the equality function. So it's 1 when the classical single bits are equal, and 0 when the classical input bits are not equal. And then it turns out there's some classical protocol for performing CDQS for this function and this secret size, which just relies on shared classical randomness between Alice and Bob instead of any entanglement. And the protocol is just that, so Alice receives X and the secret S, Bob receives Y. They share these two random bits, R0 and R1. And Alice just does a bitwise addition of the secret and the random bit which is indexed by their input X. And Bob just sends along their random bit which is indexed by their input Y. And so in correct instances where X and Y are equal, so F is equal to 1, all the referee has to do is add together the two classical bits that they receive. The bitwise addition of Rx and Ry is just 0 when X and Y are equal, and so the referee recovers the secret. On the other hand, if we're in a secure instance, so this equality function is 0, in that case, effectively the referee is just receiving two uncorrelated classical bits, random classical bits, so they can't learn anything about the secret in that case. Okay, so we'll actually be interested in a version of CDQS where we're only demanding computational security instead of information theoretic security. So in particular, we'll make the following modification. For the correctness definition, we just require that the decoding channel should be implementable by some polynomial time circuit. And for the security condition, we just need that the simulator channel should be indistinguishable from Alice and Bob's messages provided that the referee only has access to, operations of complexity smaller than some parameter t. Okay, so we've relaxed from an information theoretic requirement for security to some, computational requirement for security. There's a more technical definition, which I'll skip. That's the basic picture to have in mind. Okay, so now with all this background out of the way, we can show a result which says that if f is sufficiently non-trivial, so if it's not constant for at least some value of the input x, then a computationally secure CDS protocol with this complexity parameter t scaling super polynomially and some resource state psi has to satisfy this lower bound on the mutual information between Alice and Bob in this resource state. So it's a lower bound in terms of the size of the secret, dq, that's the dimension of the Hilbert space for the secret, and then delta and epsilon were the security and correctness parameters for CDQS. So in other words, high-performing CDQS that's very correct, very secure, and works for large secrets, it requires sufficient correlation between Alice and Bob. So just for a sketch of why that might be true, we'll just see a brief version of the argument. So suppose that we've identified some x star y star and some x star y star prime for which f evaluates to 0 and 1 respectively. And now we'll want to think about a way that the referee could learn about the secret even though they're in the secure instance where f equals 0. So the rest strategy on that input should be to take the messages they receive from Alice and Bob, totally trace out the one that they received from Bob, and then replace it by what Bob would have sent if they had instead received the classical input y star prime and applied it just to their half of the shared resource state. I guess I called it psi of b there. So the referee traces out the system they actually received from Bob, replaces it with this other system, and then they apply the decoder associated with x star and y star prime. Now, if the resource state was actually close to product, then the strategy should give a message which is very close to the message that Alice and Bob would have sent in this correct instance. So in that case, the referee should be able to recover the secret just by the correctness condition. On the other hand, because we're actually in a secure instance, we know that the referee shouldn't be able to recover something. So there's a tension there, and resolving that tension leads to this lower bound as stated here. So we can't actually be close to a product state for our resource state. Okay, before I move on to the final portion of the talk, I'll just pause and see if there are any questions. Okay, so I'll continue. Great. Okay, so now the reason that we introduced all of this, baggage related to quantum cryptography is that we're now going to imagine embedding this conditional disclosure of secrets primitive into some holographic CFT2 by, imagining that different parties appearing in this CDQS have access to different space-time regions, and the causal structure associated with these space-time regions is going to enforce the required pattern of communication for this CDQS prescription. So in particular, we'll imagine that this referee is constrained to some causal diamond, R hat, and then Alice and Bob are going to respectively receive their inputs x and y at two different space-like separated input points, C1 and C2. And we imagine that Alice and Bob are able to act or operate within two different decision regions, V1 and V2, which are defined as the intersection of the future of their individual input point with the past of R and the past of R complement. So this is capturing the idea that Alice and Bob can, receive information from their input point, apply some operations, and then send some of the information to the referee, but also trace out some of the information by sending it into the complement of the referee. Okay, so that's how we would embed CDQS into some holographic CFT2. And now we should note that by fixing these space-time regions and some CFT state, what we're doing is implicitly constraining the different choices of parameters, n, nq, delta, epsilon, and this function f for which CDQS would be possible, given that choice of space-time region and that choice of CFT state. Now, in some cases, we can get some direct insight into, for which parameters CDQS is possible by appealing to this bulk perspective. So, in particular, we can argue that there should exist a nice, simple local protocol that exploits the fact that there's this dual bulk description, and we'll always be thinking about some semiclassical limit where g equals 0, or g is going to 0. So the cases where we can argue for the simple local bulk protocol are cases where we have some non-empty bulk scattering region, which is defined as the intersection of the future of Alice's entanglement wedge with the future of Bob's entanglement wedge, with the past of the referee's easy to reconstruct wedge, and the past of the referee's not easy wedge. So whenever this bulk scattering region is non-empty, we can see that in principle that this causal structure is consistent with Alice and Bob being able to send their inputs, x and y, along with the secret, through the bulk to some scattering point where the function can be evaluated on the inputs, and then one could either send the secret into the easy to reconstruct region if we're in a correct instance, or the not easy to reconstruct region if we're in a secure instance. So it seems like whenever this bulk scattering region is possible, we expect that there should exist some protocol to perform CDQS in the boundary. Yeah.
Sorry, I just trying to build an intuition here. How can the intersection between the easy and not easy entanglement wedge, pass of the entanglement wedge for the referee be not empty?
Sorry,
I would have thought that easy and the not easy are like complementary.
It's the intersection of the past of those two things.
Oh, sorry. Okay,
Yeah. We just require that there should be a bulk scattering point where you could either send the secret into the easy to reconstruct region or outside of the, like the space like complement of the easy to reconstruct region. Thanks. Great. Okay. So it seems intuitively from the bulk perspective that whenever this region is non-empty, there should be some protocol to perform CDQS. But we should note that in order for this protocol to be viable, we have to make some assumptions about the different parameters that are appearing in this definition of CDQS. So in particular, we have to have these inputs, the classical input and the quantum input, be sufficiently small so that we don't have to worry about back reaction. There's also a question of how small we can take these correctness and security parameters. So certainly the correctness parameter should just be like the correctness parameter for ordinary HKLL reconstruction. It's telling us about the correctness of our reconstruction in these, f = 1 instances where we're just throwing the secret into the easy to reconstruct region. So in particular, that's non-perturbatively small. And then delta is going to be the bias in the success probability for low complexity reconstruction by the referee. And that's what we were talking about in the context of these tensor network models earlier on in the talk. So in a bit more detail, the bulk protocol is going to be consistent with the following choice of these various parameters. So for the delta parameter, we're going to say that in this case, the bulk spacetime region X that I was mentioning earlier, that we're imagining hiding the secret into, is just going to be defined by the future of the scattering region. So that this is the part of the spacetime that that the inputs could be received from and then sent into. And we've argued on the basis of this tensor network model that the bias in the success probability for reconstructing something inside of this region should be given by this exponential in minus delta S gen X. So this generalized entropy difference, in the classical case an area difference, associated with this restricted bulge surface and the appetizer surface. Then this dq we can take to be little o of minus log delta. In particular, this will ensure that it's small enough that it doesn't back react. And then epsilon, all we have to know for our purposes is that it's going to be smaller than this dq term. So now it turns out that importing all of these assumptions into the lower bound on the correlation in CDQS that we mentioned before, we arrive at the following claim. So the claim is that whenever this 2-to-2 scattering region is non-empty, the mutual information between Alice and Bob, as computed by the Ryu-Takayanagi formula, should be lower bounded by this area difference between two surfaces that are homologous to the referee's region R. So one is the restricted bulge associated with the future of the scattering region, and the other the usual appetizer surface. This comes along with some universal proportionality constant, which is not fixed by the argument that I just gave. And something to emphasize is that this is totally just a geometrical constraint because the mutual information can be computed by the Ryu-Takayanagi formula. Can I ask how I'm doing for time? Oh, sorry. Oh, great. Okay, perfect. Thanks. Okay, so all of this discussion has landed us on this particular claim about holographic spacetimes. So we won't be able to prove that claim in generality, but what we'll try to do instead, a more modest goal, will just to be to give some basic consistency checks on the plausibility of that claim. So the first consistency check is just a parametric consistency check, and it's that whenever this 2-to-2 scattering region that we talked about is non-empty, it's going to imply that we have order 1 over g Newton mutual information between Alice and Bob. So the argument for this is just, for people familiar with this connected wedge theorem, it's basically exactly the same. The assumptions implicit in this argument are that we have some asymptotically globally ADS3 spacetime that's satisfying the null energy condition. And now to argue by contradiction, we imagine that V1 union V2 actually has a disconnected entanglement wedge. So here V2 and V1, these intervals, are assumed to have a disconnected entanglement wedge, which corresponds to the union. So the RT surfaces are just this union of gamma 2 and gamma 1, homologous to the individual boundary regions. And now one could argue that when this 2-to-2 scattering region is non-empty, one can construct a null membrane, which consists of shooting forward some ingoing null sheets from these surfaces gamma 1 and gamma 2, so that these null sheets will meet at some codimension 2 surface, which we call the ridge, this R quantity, and then shooting back some null sheets from this appetizer surface. So that gives rise to these light pink sheets shown here. And in the case that this 2-to-2 scattering region is non-empty, this null membrane is guaranteed to have essentially the topology shown here. So this ridge is, got some non-zero area. And then by applying the focusing theorem, so focusing upward along this membrane and then downward along the past of this gamma app, we can construct some new candidate RT surface, which is homologous to this boundary region V1 union V2, but has strictly smaller area on the initial Cauchy slice that we started on, so contradicting the maxi-min prescription. So the conclusion then is that if you do indeed have non-empty scattering region, it has to be the case that you're in the connected phase of this entanglement wedge. In fact, more than just saying that you're in the connected phase, this proof actually gives a lower bound on the mutual information shared by Alice and Bob in terms of the area of this ridge surface that appeared in this argument. So another kind of consistency check is that you can come up with a sort of, in general, strictly weaker lower bound in terms of some geometric quantity for this mutual information. So in particular, we can identify some subset Y of the region X. Recall that X is the future of the scattering region. But we can construct some subset Y so that whenever this 2-to-2 scattering region is non-empty, the mutual information is lower bounded by something that looks like the right thing, but the restricted bulge is replaced by the restricted bulge associated with Y instead of X. So I should say what this Y is. This Y, instead of being like the full future of the scattering region, or equivalently the future of this ridge, it's basically like the boundary of the future of the ridge. So this Y is defined as the future of this ridge intersected with the null sheet that you shoot forward from the RT surface for V1, and the null sheet that you shoot forward from the RT surface for V2. Okay, so that it's kind of this paper airplane looking thing in this diagram here. And okay, now the argument for this lower bound is going to be as follows. We imagine that we've identified sigma to be the partial Cauchy slice, which is appearing in the maxi-mini-max definition for the restricted bulge associated with Y. So that'll just be some partial Cauchy slice. And now we let Y1 and Y2 denote the two components of the intersection of this region Y with this partial Cauchy slice sigma. Now we have just by focusing that the area, the sum of the areas of these two components is going to lower bound 2 times the area of the ridge. So this is just because we're focusing forward from the ridge and then possibly discarding part of the result that lies outside of the not easy to reconstruct wedge. And now for this choice of Y1 and Y2, which are guaranteed in general to intersect this appetizer surface, one can actually explicitly construct some sweep out, not necessarily the actual sweep out which is picked out by the maxi-min-max procedure, but one can define some sweep out as shown. So the first surface in the sweep out is just it's going to overlap exactly with the appetizer surface, but then later surfaces in the sweep out are going to send out kind of these probes, which are so that they're going to cover part of Y1 and Y2 until the last surface in the sweep out basically is a surface which hugs y1, y2, and this appetizer surface. So it's clear that the area of the maximal surface in that sweep out, this A of f of 1, is just given by the area of this appetizer surface plus 2 times the area of y1, because we go up and down, plus 2 times the area of y2. Okay, so putting all of this information together, we have that this mutual information is lower bounded by the area of the ridge. We saw that on the previous slide. That then is lower bounded by the difference between the maximal area surface in this particular sweep out and the appetizer. That's combining this definition with this statement of focusing. And then finally, that's upper bounded by the area of the true restricted bulge surface associated with y minus the area of the appetizer. That's because of this maxi-mini-max procedure, which tells us that to get the true restricted bulge, we should do a minimization over sweep outs. So that'll land us on something smaller. So at the end of the day, given that chain of inequalities, we arrive at the previously stated lower bound for the mutual information. Okay, finally, maybe an observation we can make about this. So, we formulated this conjecture. We argued for some sort of, that some sort of weaker lower bound should be true. We could ask about whether a stronger lower bound could be true, where instead of having the mutual information lower bounded by the difference between this restricted bulge and the appetizer, it's just the difference between the actual bulge associated with the Python's lunch and the appetizer. So in other words, we could ask whether the mutual information is lower bounded by something proportional to the log of the complexity appearing in the Python's lunch conjecture. So yeah, somehow assuming that the Python's lunch conjecture was true, this lower bound would be tantamount to a lower bound on computationally secure CDQS, coming from the maximum of the referee's complexity for these secure instances. So in other words, it would say that, if we want to be secure with respect to an increasingly complex referee, we require increasingly large correlation between Alice and Bob in order to actually perform the CDQS properly. So we could ask whether that's true. It turns out it's not true, and so we find some counterexample in the situation where the referee's region corresponds to 2 disconnected intervals in CFT2. And so it turns out that permits some limit where this mutual information is vanishing in the limit, while this Python's lunch complexity is staying finite, and the scattering region is non-empty until we're actually in the strict limit. Okay, so that argues in favor of there not being a lower bound from the referee's complexity in the context of computationally secure CDQS. Nonetheless, it's still consistent with our actual conjecture, since in this case it turns out that this region X, the future of the scattering region, intersected with the not easy to reconstruct region for the referee, is actually vanishing. So the distance that they can send the secret into the not easy to reconstruct region is vanishing in this limit until, and as a result, the lower bound appearing in our conjecture is itself vanishing in the limit. The restricted bulge is just eventually going to coincide with the actual appetizer surface. So now on the quantum information side, we actually expect a pretty similar lower bound to be true. So this is that the mutual information should be lower bounded by the minimum of this log of t, where t is the maximum complexity for the referee in the security definition. But we should take that minimized also with the mutual information that would be required to perform information theoretically secure CDQS. So the minimization here is required because, basically once the mutual information becomes so large that it exceeds actually the amount of correlation required to perform totally information theoretically secure CDQS, then, we can in particular do computationally secure CDQS with arbitrarily large values of this t parameter. Like clearly once we can do information theoretically secure, we can also do computationally secure for any value of t. Now, a lower bound analogous to this is relatively straightforward to show for the dimensions of the resource state that Alice and Bob share. So it seems at least plausible that it should be true also for the mutual information, given that it doesn't seem like Alice and Bob could necessarily have any strategy that's just exploiting a lot of local randomness instead of actual correlation. So it seems at least plausible that some lower bound of this form should be true, but that hasn't been proven in general. But then assuming that it is true, it seems like the violation that we just mentioned in the 2-interval case has to be occurring in a regime where this information theoretically, or this information theoretically required mutual information is itself vanishing. So there seems to be a tension between this finding for the two-interval case and this type of lower bound. It could be resolved if this it were itself vanishing in the limit that we're considering. And it turns out that this is essentially conceptually consistent. Like we should imagine that as we're taking the limit I mentioned in this two-interval example, we are increasingly limiting the number of parameters for which computationally secure CDQS is possible until information theoretically secure CDQS can actually be performed with an amount of mutual information which is smaller than this log of C Python's lunch. So from that perspective, this quantum information lower bound seems to be consistent with what we find in this two-interval counterexample. Okay, so just to do a brief recap, because I think I'm out of time. So yeah, what we did here was to derive some new conclusions regarding the impact of post-selection in these, for low complexity bulk reconstruction in these holographic tensor network models. We tried to extrapolate these conclusions from the tensor network context to actual gravitational theories, just following the chain of reasoning behind the Python's lunch conjecture. And to that end, we gave some geometric measure of the security of information lying inside of a Python's lunch. We then proved some lower bound on the correlation required between Alice and Bob in order for them to perform some computationally secure CDQS scheme. We combined all of these arguments to formulate some fully geometrical constraint on holographic spacetimes, and we gave at least a couple of basic consistency checks for that proposal. So just zooming out a bit, like the main thrust of this talk has been to somehow try to provide evidence for the Python's lunch conjecture, like by proxy, by basically demonstrating that it gives the right kind of geometric notion of the amount of post-selection appearing in a tensor network. Because proving something about some sort of complexity theory statements in the context of gravity seems very difficult, we've taken this sort of side route of trying to argue that the Python's lunch conjecture is capturing something correct about the gravitational analog of the amount of post-selection. And so there are various, future directions that lie kind of along those general lines. So one obvious one would be to try to prove the proposal I described here, or identify some counterexample. On the quantum information side, it also seems interesting, well, for one thing, to prove the lower bound on the mutual information that I was just describing in terms of this complexity parameter, but also to try to understand whether there are lower bounds on the mutual information in CDQS involving these various parameters, security and correctness parameters, and the size of the secret and stuff, that could potentially help us to resolve the value of alpha naught appearing in this lower bound. That would hopefully allow us to get a bit more of a quantitative handle on whether certain examples of holography are obeying this lower bound or not. And more broadly, I think it's interesting to ask if there are other consequences of post-selection in these holographic tensor network models for features of entanglement wedge reconstruction, and whether combining these observations about consequences of post-selection for entanglement wedge reconstruction with the kind of cryptographic holographic task techniques that I mentioned here could possibly yield some new insights. I'll stop there, so thanks.
Are there more questions for Chris? Yes. Sorry, maybe I missed it. So what's the gravitational analog of post-selection?
Yeah, it's related to some geometrical features of the space-time. So in the context of the usual Python's lunch conjecture, in the tensor network, you can argue that this total amount of post-selection is just related to some difference in generalized entropies associated with some cuts through the network. This like bulge cut and some locally minimal cut, the appetizer. And then the claim is just that in gravity, it again should be associated with the generalized entropy difference between some surfaces homologous to the boundary region that we're thinking about bulk reconstruction on this boundary region. And that these surfaces can be identified, basically there'll be some quantum extremal surfaces which are perhaps locally but not globally minimal, for the appetizer, and then they can be defined by this maxi-minimax prescription for the bulge. So that's the claim. It's related to some kind of like geometrical bottleneck that you encounter in like some slice of the space-time.
Bag of gold or something like that?
Yeah. For example, a bag of gold would have a Python's lunch.
In general connection with black holes or, I don't know, topological defects? geometries?
I mean, certainly it is the case that most black hole spacetimes will have these Python's lunches. By topological defects, do you mean like
Maybe non-trivial connectivity of space.
Yeah, do you mean like higher genus, or what do you mean?
Well, yeah, genus is in low dimension, but higher.
Yeah, I mean
generalizations of that.
So certainly, whenever you have these multiple quantum extremal surfaces appearing, you can expect these Python's lunches to appear.
More questions? Okay. So if no, we thank Chris again. Thank you.